Ignition sequence start.
Good morning, and welcome to this view of the International Space Station Flight Control Room, the famous Mission Control Houston. These men and women are monitoring the space station systems and working with the Expedition 66 crew members as they move through the assigned tasks of the second half of their workday in space. Each day, Commander Anton Shkaplerov and his crewmates take care of their vehicle and support groundbreaking scientific research. And this week, they have also been getting ready to send 2 astronauts outside the station to prepare for some hardware upgrades.
Houston Station on Space to Ground.
Welcome to Space to Ground. I'm Shaniqua Vereen. On Tuesday, March 15th, NASA astronauts Kayla Barron and Rasha Chari will venture outside the orbiting outpost to perform IROSA 3A power channel preparations. IROSA, or ISS rollout solar array upgrades, have been ongoing since 2020. Barron and Chari will install the modification kit in preparation for the new solar array. The International Space Station has 8 power channels, each fed with electrical power generated from one solar array wing, extending from the station's truss backbone. The original solar panels launched on 4 space shuttle missions from 2000 to 2009. As expected, the solar panel efficiency has degraded over time. NASA is upgrading the space station's power system with the new rollout solar arrays, which will partially cover 6 of the station's 8 original solar panels. When all 6 IROSA units are deployed on the station, the power system will be capable of generating 215 kilowatts of electricity. Back inside the station this week, the science continued with cameras that could save your crops. Imagine if farmers could get advance warnings of water stress in their crops, alerting them to changes in crop health days to weeks before they become visible. They would be able to head off those issues and decrease chances of crop losses. A new experiment heading outside the space station aims to do just that. NASA flight engineer Kayla Barron installed the Long-Wave Infrared Sensing Demonstrator, or LISAR, on the NanoRacks external platform this week. The CUBE satellite will reside on the exposed facility of the Japanese experiment module for several months. It will test a thermal infrared sensor for taking precise measurements of Earth's surface temperature and monitor water resources. This testing is a first step on the path to launching constellations of small satellites that could take measurements around the entire globe every day. This knowledge could help farmers achieve more yield and better quality crops. That's Space to Ground. Thanks for watching. We'll see you next week.
When astronauts go outside the International Space Station, as Rasha Chari and Kayla Barron will do next week, they wear what amounts to a human-shaped spaceship. In this demonstration video, astronaut Ricky Arnold gives us a tour of the critical parts of the spacesuit that keep astronauts safe as they work in the harsh environment of space.
So we are standing in the Quest airlock, which is divided into 2 parts. We have the equipment lock and we have the crew lock. This equipment lock has a hatch right here that closes, and the crew lock has another hatch. The EMU, or the Extravehicular Mobility Unit, is our spacesuit, and it's divided roughly into 2 parts. We have the hard upper torso, which is almost like a turtle shell. It's a hard fiberglass shell, and then we also have the lower torso assembly. These spacesuits are our own little spacecraft, and they have everything you need to keep you alive out in space for 7 to 8 hours, maybe even longer, depending on how hard you're working. The only thing that they do not have, and they have radios, it has oxygen, it has carbon dioxide scrubbing, it has temperature control, it has everything you need except for one thing: a restroom. And so when we get ready for our EVA, the first thing we put on in the morning is a diaper. And that's our first layer. Then over the diaper, we put on a pair of long johns, and that's to keep our arms and legs from getting scraped up. It also provides a little bit of wicking in case you're getting really hot and sweaty. The next layer is our liquid cooling garment. And the LCVG has little tubes running through it which allow water to circulate inside the LCVG to provide cooling when we're outside working really hard. So we've got the diaper, we've got long johns, we got the LCVG, and then we're going to wear our spacesuit. 7 layers from the bladder on the inside, which maintains pressure, and that's a rubberized bladder, all the way out to the white layer on the outside. The crew member inside the spacesuit is also wearing this, what we call a Snoopy cap. It's a communications cap. We have a radio, so we can talk to not only to Houston, but we can talk to people on the space station and to each other. So we wear this communication cap inside the helmet. Also, another key component of the EMU, or a spacesuit, is the helmet. You can see the helmet has a gold visor, which protects us from the rays of the sun that we can bring down. It's pretty bright out there, and this gold visor helps reflect the rays of the sun so we can actually see and operate in daylight. At nighttime, we can raise this visor up, gives us a clearer view, and additionally, we have helmet lights built into the helmet. On top of the helmet, we also have a television camera, so the ground is able to watch us while we work through these TV cameras. The work is really all done with hands, and so our gloves are really our most important piece of equipment in order for us to work outside. And one of the real challenges of a spacewalk is you have this heavy gloved hand, which is inflated, so it wants to stay like it's blown up like a balloon. But we walk by grabbing onto handrails and making our way along the ISS. So every time you move your hand, you're fighting against a balloon that wants to inflate. And then on top of that, all of our equipment is based on using your hands too. So after 6.5, 7 hours of kind of fighting against this glove, it's a really long day, and your hands are probably the thing that are most exhausted after 7 hours out on an EVA. Well, we're going out to work. You probably saw me move this mini workstation. The way we carry our tools is on a mini workstation, which is carried on the front. Every single tool we use is tethered to us. We do not want to accidentally create satellites. Our primary way of remaining attached to the ISS, if we're not using our hands, are these waist tethers. And you can see they just have a big hook. They go around a rail or anything else on the ISS and latch on, and it actually has a locking mechanism as well to hold us nice and tight. So we always want to have one of these attached if we're not holding on with our hands as well. The back of the EMU has our life support system. The life support system contains all the equipment we need, from a UHF radio down to the oxygen tanks that provide primary oxygen. One of the challenges inside this sealed environment, it's very easy to carry our own oxygen with us, but we generate a lot of carbon dioxide, particularly when we're out there working very hard. So to combat that and to deal with that, we have these canisters called Medox canisters, which are just silver oxide. They are carried in the backpack along with a very large battery, which provides all the electricity for us. I don't have a battery here to show you today because we're in the process of charging them. We're about a month out from doing a spacewalk, and we've already started getting ready for that. So this Medox canister is able to remove about 7 to 8 hours of carbon dioxide that a human can generate inside the spacesuit. EVAs have allowed us to build and maintain the ISS, repair mission-critical hardware, investigate malfunctions, install new hardware, and the view, unbelievable. See you next time.
All station spacewalks begin by getting the astronauts into the spacesuits that support them while out in the vacuum of space. Here's an accelerated view of that lengthy process from an EVA during Expedition 61. The International Space Station is a platform in space supporting scientific investigations in a vast range of scientific disciplines, and that includes astronomy. The Neutron Star Interior Composition Explorer, out on the station's truss, was recently used to observe the merging of multi-million degree X-ray spots on the surface of an isolated neutron star, the crushed core of an exploded sun 13,000 light years away from here. The International Space Station is designed to be a laboratory in space that can provide benefits here on Earth and teach humankind what we need to know to be able to explore beyond low Earth orbit in the years to come, including our return to the Moon in just a few years. A couple of recent experiments on the station have been building on all of those goals.
Cementing our place in space. Presented by Science at NASA. As your dog drags you around the block for his morning walk, you're probably not thinking about the wonders of the neighborhood sidewalk. But that concrete is pretty great. Next to water, it's the most widely used material on Earth. In the future, concrete may be equally useful off the planet, when humans construct a permanent base on the Moon. They'll need sturdy stuff that can weather bombardments from solar radiation and meteorites. No one wants a crack in their moon base. The key to making out-of-this-world concrete may be to study it out of this world. 2 experiments have taken place aboard the International Space Station, or ISS, to do just that. The Microgravity Investigation of Cement Solidification, or MIX, and Multi-Use Variable G Processing Facility, or MVP Cell 05. Researchers from Pennsylvania State University and NASA's Marshall Space Flight Center are analyzing the study's results. Concrete is a mixture of sand, gravel, and rocks glued together by cement paste made of water and cement powder. And it's not as mundane as it looks. Under the surface, it's quite complex. What goes on there is key to its strength and durability. Yet scientists still don't understand all the details of concrete's chemistry and microscopic structure. Processing methods aren't cast in stone. There's plenty of room for improvement. Alexandra Rudlinska, principal investigator for both experiments, says, "Our experiments are focused on the cement paste that holds the concrete mixture together. We want to know what grows inside cement-based concrete when there is no gravity-driven phenomenon, such as sedimentation. It all begins when water is added to the cement. To put it very simply, the cement's molecular structure changes when the cement grains dissolve. Redlinska explains, as the old molecules dissolve, calcium silicate hydrate and calcium hydroxide start to crystallize. Myriads of these tiny crystals form all through the mixture, interlocking with one another and with the other concrete ingredients, such as gravel. The ISS experiments are researching how this all plays out in space. Redlinska says it could change the distribution of the crystalline microstructure and ultimately the material properties. The ratio of the water-cement powder is critical to making the concrete components combine effectively and determining the strength and durability of the final concrete. Will this ratio need to be different on the Moon, where gravity is about 1/6 of Earth's? That's the kind of question the experiment will shed light on. For the mix experiment, astronauts added water to a series of packets containing dry cement powder, then added alcohol to some of the packets to stop the hydration process at specified times. For MVP Cell 05, astronauts also hydrated dry cement, but for this experiment, they used a centrifuge on board the ISS to simulate gravity at a number of strengths, including lunar gravity and Martian gravity. For both experiments, the samples were returned to Earth for analysis. We're already seeing and documenting unexpected results, says Marshall's Richard Grugel, co-principal investigator for MVP Cell 05. Redlinska adds, what we find could lead to improvements in concrete both in space and on Earth. Since cement is used extensively around the world, even a small improvement could have a tremendous impact. We might even end up with better sidewalks for walking our dogs. For more from the International Space Station, go to www.nasa.gov/ISS-science. For information about other weighty matters, visit science.nasa.gov.
NASA's Artemis program will return Americans to the Moon in a few years and help get us ready to go on to Mars. So knowledge of the geology of both locations will be important. Recently, the next-to-last man on the Moon, Apollo astronaut Harrison Schmitt and astronaut Jessica Watkins, who is just a month away now from launching to the International Space Station on the Crew 4 mission, met up at the Johnson Space Center's Moon Rock Lab so the two geologists could discuss how what we learned from Apollo will inform our efforts in Artemis.
Sample of both sides. I wouldn't bet on it. Okay, I just got a chunk of that side.
They have what I consider one of the most important.
Can you talk about kind of what went into your sampling strategy and how you chose which samples to bring back?
The idea was to get as broad a spectrum of new samples as we possibly could, and that turned out pretty well. We did. And in fact, we sampled at least ejecta, what we call melt ejecta from 3 major basins, maybe 4. We sampled fragments that almost certainly came from the deep mantle of the Moon. We didn't know that at the time. That's only recently that we figured that out. And that we also then added to our broad knowledge and history of these volcanic eruptions that have occurred on the Moon over time. Now, when you go to the Moon on the way to Mars, Jessica, that education I think you're going to get on the Moon will be very relevant to Mars. But Mars, of course, does not have that micrometeorite impact environment that we have on the Moon, because it has a small atmosphere, about 1/100th of that of the Earth, and that filters out the small impact. The main weathering process on the Moon are these micrometeorite impacts and solar wind spallation of the surface. Solar wind's made up of high-energy particles, so they actually erode the surfaces of rocks as well as change the character of the debris layer on the Moon. On Mars, the dominant erosive force is wind.
Yep.
And so if you're used to studying geomorphology here on Earth that involves wind.
You're in good shape. Yeah.
You can learn a lot
Right.
about what you're going to see on Mars. But all of that comes from studying the moon.
Right.
If we hadn't had the moon, we wouldn't understand this early history of the Earth or even speculate about what it might be, speculate intelligently anyway,
Right.
about what it might be.
Astronauts are public figures, and much of their history is well known, but not all of it. So before they launched, we grilled the astronauts who flew to the station on the NASA SpaceX Crew 3 mission, Raja Chari, Tom Marshburn, Caleb Barron, and Matthias Maurer, in order to discover the truth about their favorite foods, guilty pleasures, and what these explorers would do with a day off on the moon.
3, 2, 1.
Star Wars. Stanley Kubrick's 2001: A Space Odyssey.
Probably Life is Beautiful or Amelie.
Master and Commander.
Ooh, depends on the era of my life. I'd probably say Dune, though, overall.
Daniel Burstyn's The Discoverers.
The Perfume.
The Rick Atkinson Army at Dawn series.
Just relaxing.
Playing with my kids.
Backpacking.
Backpacking.
That would be probably peanut butter.
Pizza.
That's a hard one. I like almost all food.
Fall.
Fall.
Fall. French horn.
Acoustic guitar. That was easy.
Guitar, but I have lack of talent. Practice a lot, but failed.
Pesto.
I think on choice, I like pizza Napoli.
Tomato and pepperoni.
I like a spicy Italian sausage.
Swimming. Water polo. Anything in the water.
I'm bad at many of them. Probably kickball with my kids.
Well, it's football, European football, cycling, swimming.
Track.
Coffee.
Tea.
Definitely coffee.
Both.
Dancing.
Singing.
I think I'm really bad in dancing.
Ooh, I have two answers for this. Probably learning Russian, challenging for me, and definitely spacewalk training.
NBL or spacewalk training.
Speaking Russian while in a spacesuit underwater.
Oh, waiting for the mission.
Oh, definitely look at rocks with Jessica Watkins.
I'd go on a buggy ride.
I would be skipping and running and climbing any crater I could find.
Well, first I would like to jump as high as I can to prove that I can jump 6 times as high as on the Earth. And the second thing I would do is I would try to explore a moon cave.
Would be flying.
To pacify the world.
To time travel.
Frappuccinos.
Eating ice cream, way too many.
Cookie cake.
I would say never close a door on yourself. Like, don't self-select out of opportunities. Like, you have to put yourself out there if you want to pursue your dreams.
Keep at it. Stay persistent. Don't worry about it. It's going to be okay.
Just relax and enjoy the moment a bit.
I'd like to do another spacewalk.
I'd love to do a spacewalk.
Doing a spacewalk.
Well, flying to space is the first, doing an EVA is the second, and hopefully walking on the moon is the third.
I won't go into specifics, but it all has to do with using the bathroom.
Robotics technology originally developed for the International Space Station has found a way to help humans here on Earth in the operating room. The company that developed and built the Space Station robotic arm has worked with a medical device manufacturer to create an automated robotic arm that tracks the movement of a surgeon's tools and helps to expedite brain and spinal surgeries.
The International Space Station is probably the most fantastic vehicle ever built.
It's a one-of-a-kind laboratory orbiting about 250 miles above the Earth.
And we perform experiments on the International Space Station.
We can do science, we can do experiments, we can learn how to do things out of this world.
And the result will help benefit the people on the ground.
So not only that, but we're also seeing benefits of how we actually assembled the space station.
So the International Space Station in its design was essentially designed like a Lego toy. Lots of big pieces that need to be put together. Some of these pieces are going to be about the size of a city bus.
We needed a way of manipulating or moving these big pieces
and very precisely putting them together.
Canada worked with its contractor, which was MDA, and with that company came up with a design that was going to meet the needs of the International Space Station.
The solution to that was using a fairly large robotic arm, and that system ended up being Canadarm2. It could move around the space station, grab payloads, move them to where they needed to be so that the space station could be assembled.
You couldn't have built a vehicle like the International Space Station without a robotic system like this.
And that was when we started talking to Synaptive Medical.
Knowing that MDA has done this before in space, we thought it would be very easy for them to bring that experience and that technology into the neurosurgical area and help us with our medical robotics. We worked with MDA to create Drive. Drive is a robot mounted onto a base that holds a surgical camera that can be automatically positioned to any surgical instrument that's tracked by our system.
What this arm does, it follows you and it tracks you, so it speeds up efficiency.
Ultimately, using the Drive system allows the surgeon to have shorter surgical times, which means shorter recovery times for the patient, and ultimately that's better for the hospital and the patient.
But what the robot does for us is that it allows us to do it safer. You can do it better with less harm to the patient.
The software that runs on the Drive system is directly derived from the software that runs the Canadarm2 on the International Space Station.
Those robotics work with and alongside an astronaut to enhance what they do. So that connection is a very direct and real one.
Right now, it's probably the most used system that we could say is derived from the things we did on the space station, and we're pretty proud of that.
And I've seen the arm before, we've seen it on the space station, but I never put the two and two together that I'd have the same arm in the OR at some time now.
I think everybody has this dream of how robotics are going to become more and more a part of everyday life. The things that we do with robotics on the space station is basically pushing those dreams forward. And we evolve the system, we gain the knowledge, we gain the experience, the expertise. So this is kind of the unexpected benefits that we get out of doing a program like the International Space Station.
If you want another look at any of the stories we showed you today, you can get one right over there on YouTube and Facebook at those addresses. You'll find them there along with lots of other great features on a whole variety of NASA topics. And if you're looking for good conversation about human spaceflight, check out Houston, We Have a Podcast, our weekly show about all aspects of human spaceflight and NASA's missions of exploration. Today, Gary Jordan learns about the Near-Earth Asteroid Scout mission, which is flying on the SLS rocket on Artemis 1, and the enormous solar sail it will employ in order to navigate into the neighborhood of an asteroid for a comparatively close-up study. Go to nasa.gov/podcasts for this week's episode. You'll find all the previous episodes there too, as well as the full library of all the NASA podcasts. And they're all on Apple Podcasts, Google Podcasts, and SoundCloud too. You can get the latest from all over NASA delivered to you every week. Go to nasa.gov/subscribe to sign up for the NASA newsletter.